So today we will discuss about design of gears, right? And we will not focus on those types of gears and terminology used in gears and all, because that we have already discussed during that theory of machines, right? So we will start what are the forces acting on this gears while in working condition, right? So today we will mainly focus on spur gears, right? So, as you can see here in this particular figure, the forces are mentioned whenever two or a pair of teeth of gears are in mesh with each other, right? So, the force is acting along the pressure line as this Pn mentioned in this figure, right? So, this particular force is then actually going to provide those two different components in two direction, right? One is in tangential direction and other is along the radial direction, as it is mentioned in that figure in the right, like components of this tooth force. So here as you can see, this tangential force and radial force are acting right in this particular gears, on both the gears, means on both the gears, or we can say on pinion and gear, right? Generally this driver is known as pinion, right, as it is already mentioned here, right, and this driven is known as gear, right. So this figure shows how are the forces acting on this pinion as well as on gear. As this driver is going to apply the force in this direction, here in this gear, the direction of force is along the direction of rotation, right? While here, in case of pinion, it is opposite to that of the direction of motion, because it is the reaction provided by the gear tooth on that pinion tooth, right? So this is how we are having the forces acting on this particular teeth or a pair of teeth, right, which is in mesh with each other. So if we want to have the torque transmitted while this particular gear pair or the teeth are in mesh with each other, then we know that, right, how the torque is transmitted when these teeth are in mesh with each other. It is given by this formula, right, the 16 into 10 raised to 6. Power we are considering it in kilowatt, right, and divided by this 2 pi n. So actually, as we know that power is equal to 2 pi nt by 60, so from that only this equation has come, right. This mt is nothing but the torque transmitted by gears, torque transmitted by gears, right. It is in Newton mm. That is why here this 16 to 10 raised to 6 is there. Otherwise we are directly writing it as power is equal to 2 pi nt by 60, right. So here this torque transmitted is in Newton mm, and this kilowatt is nothing but the power, right, transmitted by gears. This is power transmitted by gears, right, and this n is nothing but the speed, right, speed of rotation mentioned in rpm. Right, so this is how we are having the torque transmitted while two gears are in mesh with each other. As we've seen in this particular above mentioned figure, this force Pt is the tangential force, right, and it is acting at the pitch circle radius, right, because as you can see here what is mentioned is pitch point, right. So this radius must be pitch circle radius. So we are assuming that these forces are acting at each point at pitch circle radius, right. So by having this assumption, how we can represent this torque
PT into R.
PT into R, correct, exactly, or PT into this T dash by 2, right? So this is how this tangential force can be represented, right? Now similarly, when more force is acting, right, if you look at the given geometry or given figure, this PR, right, PR is this radial component of this particular force, right, which is acting along this pressure line. So this PR, if we consider the same component here, right, so in this triangle you can write that tan alpha is equal to PR by PT, correct? If you observe this particular triangle, right, then in this triangle this tan alpha is equal to PR by PT. So basically PR can be represented with PT tan alpha, right? And similarly you can also write for Pn, right? So for that, let me rub this so that it is more clear, right? Now you know which triangle we are discussing. So in the same triangle, this Pn also can be represented, right? Because this Pn cos alpha will be equal to this tangential force. So from this, if you know the tangential force, then you can calculate that radial force and this force along this pressure line both, right, by this relation, right? So you can have this Pn and PR. Already we have mentioned how we can calculate this PR, right? So while calculating all these forces, there are certain assumptions, right, which we are making. So if we note down those assumptions, then as the point of contact moves, actually Pn changes, right? But this effect we are neglecting, right? So as the point of contact varies, Pn also varies, right? But this effect is neglected. Right. Some other assumptions are only one pair, right? Only one pair of teeth are in contact. There may be more than one number or more than one pair of teeth can be in contact at a particular point of time, right? And
Yes, sir. Generally 1.6 units, sir.
yeah, correct. So uh, one more assumption is it is valid under static condition, right? These assumptions are there, right? So this is how we are having idea about what are the different this loads acting when these two teeth or two or a pair of gears are in mesh with each other, right? So once you have this idea, then this FBT of forces is again nothing but how this pinion and gear are imparting force on each other, right? So one important thing to notice here is this tangential force is only taking part in this transmitting force, right? While this PR is actually known as separating force, right? As you can see, this PR is acting towards the center of the shaft on which gear is mounted, right? And it is shifting this gears away from each other. So that is why this PR is nothing but separating force, right? So once we have idea about all this, then we can first go through what are the different gear tooth failures, right? So in gear tooth failures, generally whenever these gears are in mesh with each other, very high stresses are acting at surface, right? So most of the times the surface wears are the criteria, right, under which this gear tooth are going to fail, right? So if we note down the broad uh, reasons for this gear tooth failure, then there are different wears, right, like abrasive wear, then corrosive wear, right, then this initial pitting, and this destructive pitting, right, and scoring. So if we discuss about this each different types of failure, right, one by one, then first let us see this abrasive wear. So what happens in abrasive wear is basically some foreign particles are there in the lubricant, right? So it may be some dirt, rust, right, weld spatter or any metallic debris, right, in this lubricant, and because of that the surface is going to get weird, right, because this operation is going at very high RPM, and all this debris is going to damage the surface, right? So in order to avoid this failure, uh, oil filters can be used, right? So if we go to the next one, that is corrosive wear. So it is caused by some corrosive element, right? Actually some external contamination or some extreme pressure conditions, right? All these things are going to lead to this corrosive wear, and in order to avoid this corrosive wear, we need to provide some complete enclosure or something like that, right? So it actually goes due to some corrosive elements, right? And in order to avoid this, we can provide some enclosure, right? One sec. So once we have idea about this, then our next criteria of failure is this initial pitting. Right, this initial pitting is actually a localized phenomenon. Right, and it is because of some small pits, right? And see, in order to avoid this, we need to do this precise machining of this gears, right? It is because of some small pits, and in order to avoid this, precise machining is required of gear tips specifically, right? So, and the remaining destructive pitting and scoring will discuss, right? So destructive pitting is because of some exceeded, means whenever that surface endurance strength is going to be exceeded, right, at that time this kind of destructive pitting takes place, right? It is a surface fatigue failure, right? And it actually depends on the magnitude of Hertz contact stress, right, and the number of cycles. So in order to avoid this destructive beating, the wear strength must be greater than the static plus dynamic load. We will see what is this static and dynamic load, right? And the last is scoring. So in case of scoring, what is going to happen is, here some excessive surface pressure, right, is going to
So
result.
what is head's contact stress?
Sorry.
What is that head's contact stress?
Heights context stress is actually whenever there are any stressed contact between two surface, right? At that time, this Hertz context stress comes into picture. This also we will discuss how this particular Hertz context stress can result in a wear failure. While discussing that wear strength of the gear tooth, we will see how this Hertz stress contract are applied on the surface, or at the point of meeting of or matting of these two gear teeth, right? So for now, okay.
Okay, sir.
Okay, so now in case of scoring, what happens is sometimes this excessive surface pressure or high surface speed, right, or inadequate supply of this lubricant, this all reasons may end up in the breakdown of the oil film, right? It may be excessive surface pressure, right, or this high surface speed, right, or inadequate supply of lubricant. So actually all these three reason may end up in breakdown of the oil film. Right. So what happens due to this is, because of this breakdown of the oil film, there is direct contact between this matting surfaces of the pinion and gear, right? So because of that, there are some surface irregularities, right, like this actually. All the surface which we are seeing with naked eyes as this flat surface are not actually this flat surface. There are this kind of irregularities, as it is mentioned here. It is exaggerated, but it is in the micron level. So this kind of surface irregularities are there on every surface, right? When we look it with some high resolution microscope or those kind of devices, it will be visible, right? So when this breakdown of this oil film results in contact of this pinion and gear, right? So what happens is, because of this, there will be some sticks slip phenomena, right, and which results in alternate welding and shearing. So because of that, the failure will take place. So this can be avoided by reducing the surface temperature, right? So what can be done to reduce the surface temperature is, sometimes fins are provided, right, outside the surface of gearbox, or sometimes some fan is provided for forced circulation of air. So basically, to avoid this, fins may be provided, right, on the surface of gearbox, right, or sometimes fan can be provided for forced circulation of air. So these are the various types of failure and some of the remedies in order to avoid this kind of failures, right?
Sir, sir, in corrosion wear, what are the corrosion elements?
Sorry,
Oil, sir, corrosion elements.
corrosive elements may be anything which can lead to increase in the surface area contact, right? So because of that, this uh, corrosion can take place of surface, right? So this is how this corrosive failure takes or comes into picture, right? So we'll see, right, all those things. So right now, if we go to this next, uh, this beam
Sir,
strength, yeah,
excuse me, sir.
yes,
Sir, actually scoring occurs at high temperatures.
yes, scoring occurs at high temperatures, or because see that lubricant may gets less viscosity at higher temperature. So because of breakdown of that lubricating oil, surface to surface contact will occur, right? And because of that, that scoring will take place. So in order to avoid that, we are reducing the bulk temperature, right?
Yes, sir.
So this is how uh, what we can say the remedy for reducing the scoring, right? So and this corrosive elements also, as someone has asked, it may be because of some extreme pressure conditions, right, and some external contamination. See, corrosion is nothing but the oxides formation, right? So some external contamination is there, then those corrosive elements can be formed on the surface. Is it okay?
Yes, sir.
Okay, okay. So now if we go to this beam strength, right? So this beam strength is actually presented by this Wilfred Lewis, right, in one of his paper presented in 1892, right? So what he assumed is he has assumed this gear tooth as cantilever as mentioned in this figure, right? And he has also made one more assumption in order to have that uniform strength across the gear tooth. He has assumed this parabolic beams as mentioned in this particular figure, right? So with these assumptions, if we want to calculate the strength of this beam, then as mentioned here in this particular figure, this if we look at this cross section xx, right, then at this cross section the bending moment can be given by this tangential force into that height of the teeth, right, that is h. So this bending moment can be given by this, then this moment of inertia of this particular area is given by bt cubed by 12, right, and the distance from the neutral axis is t by 2. So once you have all this data with you, then you can calculate the bending stress or maximum bending stress in this particular cantilever beam, that is given by mby upon I, right, from the theory of pure bending. So mb, all these values you can put in this equation, right? So once you put all this, then you can come up with the bending stress. And this bending stress is nothing but this bt into h into u. I guess we can directly go because this t by 2 can be cancelled, right? So here this bt square into 6, right? So if we want to calculate the tangential force which can be sustained by the gear tooth which are in mesh with each other without undergoing any failure, then we know the bending stress, right, or we know the stress which can be undergone without any failure, right? So if we convert this equation in terms of this tangential force, then it is equal to this B sigma B T square by 6h, right? Now if I multiply and divide this particular equation by m, then it is nothing but this mb sigma b t square by 6h m. Now this particular t square by 6h m is known as Levy's form factor, and it is denoted by y. Right, it is nothing but Levy's form factor. So this is how you can provide this Pt is equal to mb sigma b y, right? So in this equation, actually corresponding to the applied tangential force or transmitted tangential force, you can calculate the what is the amount of bending stress is going to be generated, right? And as we know that when this stress is going to reach the permissible magnitude of bending stress, right, when this stress reaches permissible magnitude of bending stress, then this Pt is known as beam strength, right? Then Pt is known as beam strength, right? So actually then this beam strength can be mentioned or denoted as SB, right? So then in that case you can represent this beam strength with this mb sigma b y, right? So in order to avoid any failure, this SB must be greater than the P effective. We'll also see how we can calculate this effective load, right? But for now this must be greater than the P effective. Right, so this SB must be greater than or equal to P effective. Right, now as we know that this module and this face width, this B is face width, right? This is module, this is face width. So in cantilever beam, that particular only 2D area is visible, right? The third dimension will be this face width. So this module and face width are similar, right, for both pinion and gear. So in that case the deciding factor will be this sigma b into y. This is deciding factor, right? So this particular factor is decide that which particular component is weaker between this pinion and gear. Right, so you need to calculate the sigma by product, right, if you want to know that which particular component is weaker. If this pinion and gear both are made of same material, if both are made of same material, right, then this pinion is weaker, right, always. The pinion is weaker than gear. Right, so this is how we are having okay. I have already admitted that particular student, I guess. So now so based on this, actually we can calculate the beam strength, right, and it is related to this static load, right. We have mentioned the static load and dynamic load while discussing that this destructive heating, right, that wear load must be greater than the sum of static load and dynamic load. So this refers to the static load, right, for now. So once you have idea about all this, then we can go further for this permissible bending stress. Actually, in order to have idea about the permissible bending stress, this kind of setup is made, right. This driving gear and driven gear is separated by this idler gear. So this is the stress cycle acting on this different gears. So what happens is, in as we are having this driving gear and driven gear rotated in the same direction, then for both driving and driven gears, the stress cycle will be like this, right. At a particular point of time, the stress is going to act, right, for a limited period of time. It is for a particular pair of teeth, right, which are in mesh with each other, right. So for that particular pair of teeth, this kind of stress cycle will be followed, right. And in case of this idler gear, that particular pair will undergo this stress cycle. So this is the nature of this repeated stress cycle, right. This all we have discussed while discussing design against fluctuating load, right, because it is cyclic stress is acting. So this particular nature is repeated stress cycle, and this one is a reversed stress cycle. So we know how this mean stress and amplitude stress are acting in repeated stress cycle and reverse stress cycle, right. So for repeated, the sigma mean is nothing but sigma max by 2, right. Similarly, sigma amplitude or stress amplitude is also sigma max by 2. Why? Because sigma mean is nothing but sigma max plus sigma mean by 2, and the stress amplitude is nothing but sigma max minus sigma mean by 2, right. So this mean stress and amplitude stress are given by this in case of this repeated stress cycle, while in case of this reversed stress cycle, it is represented by this sigma m is equal to 0 and sigma a is equal to sigma max, right. So once you have idea about all this different types of cyclic stress, then we can consider why these things are important to discuss, right. So this particular discussion will lead you to have idea about the this bending strength, right, which we were discussing. So this particular endurance limit, this endurance limit stress is generally taken as this ultimate tensile strength divided by 3 in most of the cases, right. And in case of bronze gears, it is generally 40% of ultimate tensile strength. So this is how this bending stress or permissible bending stress can be considered. Right. Now, once we have idea about this, what we can say, permissible bending stress, then we can go for this effective load on this gear tooth, right? So, this there are various load acting on this tooth, right? That static and dynamic load, as we have discussed, right? And whenever we are applying any load on this gear tooth, then there are what you can say, fluctuating torque acting on these gears, right? Because every time the torque transmitted is not same, right? If you if you must have idea that in case of this IC engine, torque transmitted is not same throughout the cycle, right? So the same thing will happen to this gear trains also, right, which is transmitting the torque. So what happens is we have to consider some service factor, right? So that service factor this CS is going to take care about this, right? This maximum torque upon the rated torque, right? So this basically, as we have already discussed, this MTS torque, right? So it is MT max upon this MT, or in terms of this tangential force, it is this PT max upon this PT, right? Now, in case of electric motors, as we know, starting torque is very high, right? So for them, this surface factor is decided by the starting torque upon rated torque, right? So this things are standardized actually based on this what we can say, normal load, then medium, and then heavy duty. So for all this, there are various service factor is decided at both ends. It may be, there may be fluctuation at driving end or driven end. So based on that, the different service factors are being utilized, right? So yes, so the thing which we need to consider is the service factor while we are considering that tangential load, right? Now, after that, one important thing is this dynamic load, right? So as we know, whenever this gears are in operation, there must be some this dynamic loads are acting, right, on it when they are in mesh with each other. So there are various ways of considering this dynamic load. So basically two methods are there, right? So one is need to consider velocity factor, right, in the primary stage of gear design. Velocity factor, right, in the primary stage of gear design. Or what we can do is this precise calculation, right, by Buckingham's equation in the final stage of gear design. So any of the thing can be done. Right, by Buckingham's equation. In the final stages of gear design.
Sir,
Yeah.
If torque may varies, we consider the service factor for varying of the torque may be varies due to the change in the radial load, sir, the tangential load, sir.
Sorry.
Why torque is fluctuating, sir? Due to the variation of the tangential load, sir.
No, actually, at the source it is not continuous, right? Most of the times, because of fluctuation at the source, there may be fluctuation in the transmission of that particular torque, right? And because of that, transmission load, which also being transmitted, it also going to vary, right?
Okay, sir.
Okay.
Sir, actually, is it due to the contact time between the gears? The variation of stress is based on the key.
No, no, not related to time. It is basically whatever this torque or force, tangential force, is being transmitted is not same throughout the operation time. It may going to vary, and based on how it is going to vary, at what end it is going to vary, whether it is varying at the driver end or whether it is varying at the driven end, and in what amount it is varying. So all these things needs to be considered while deciding that service factor, right? So every time it is not that is simply at a particular constant torque and constant speed, this torque is being transmitted from one gear to other gear. Are you getting what I'm saying?
So, which means if there is uniform torque, hypothetically, then no stresses. Sir.
No, 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 stress is not. The service factor needs not to be considered. Stresses will definitely be there. The service factor we need not to consider if there is a constant torque is being transmitted. Okay.
Yes, yes, sir. Actually, the stress cycles were there also.
Yeah, yeah.
Those are based on the contact.
That is different thing. This stress cycle and all these things. Stress cycle is because what stress cycle we have seen is because we are considering only a particular pair of teeth which are in mesh with each other. So stress cycle means during one revolution that pair will be in contact with each other for a particular point of time, once only. So there is that one peak is there in that cycle. So during that point, they will be under stress, and during the remaining revolution of the gear, there will be no stress.
Yes.
Okay. Okay. So I guess it is clear, right?
Yes, sir.
Okay. Now, what we need to do is if we discuss this both methods one by
So,
one. Yeah.
primary stage and final stage, do you mean that for the initial calculation, we'll be considering the velocity factor and like that?
See, we will discuss this right now. We will see when you are going to use this velocity factor, when you are going to use this precise calculation in order to calculate the dynamic load, right?
Okay, sir.
Okay. So now, if we first start with this velocity factor, right? Then there are various what we can say conditions, right? uh, in which we need to consider various velocity factor, and this velocity factor is denoted as the CV, right? Velocity factor, as we have considered the service factor as per the fluctuation in torque supplied. Here we are going to consider this velocity factor, right? And we will see for what different cases we need to consider this factor with which particular expression, right? And this velocity factor is developed by Barth. This is developed by Barth, right? So now we will see what is the condition, and in that condition what velocity factor we need to utilize, right? So here if we go for ordinary and commercially cut gears, right, made with foam cutters, right? And let us say this pitch line velocity is less than 10 meter per second. In this case, your CV is decided by or considered by 3 upon 3 plus V, right, where this V is pitch line velocity. This pitch line velocity is nothing but this pi dn by 60, right? This V is nothing but this pi dn by 60. If d is in that diameter and you want to convert it into meter per second, then you can divide it by 10 raised to 3, right? So this is the first case where you are going to consider your velocity vector with this 3 upon 3 plus v, right? So once you have idea about this, then we can go for the next case where this teeth are accurately hopped, right, and generated, right? So accurately hopped and generated gears, right, and where pitch line velocity is less than 20 meter per second. So for that, this particular velocity vector is considered as 6 upon 6 plus v. See, these are all the things based on experiments, right? So they have established these empirical relations that with this condition we can consider this velocity vector as 6 upon 6 plus v, right? Now, one second. So yeah, so the next case is that if we have precision gears, right, with manufacturing process like shaving, grinding and lapping operations, right, and velocity greater than 20 meter per second. So in that case, this CV is mentioned with this 5.6 upon 5.6 plus under root of v, right? So this is how various cases, and in those various cases what we need to consider for velocity vector, right? So now the effective load actually between this meshing teeth, effective load is actually considered with this equation.
So what you have written before grinding?
Sorry,
What you have written before grinding, is it shearing?
shaving is also surface finishing operation.
Oh, okay.
Okay. So this effective load and this tangential load is actually related with this expression, right? Effective load is equal to the CS into PT upon CV, right? CS, as we know, the service vector, CV is velocity vector, right? Now if we go for that second method, right, then in that second method, this P effective is given by CS PT plus PD, right? So now here this actually PD is nothing but this incremental dynamic load, right, which is given by the Buckingham. It is incremental dynamic load. See, because beyond this baseline velocity of 20 meter per second, this velocity factor is not going to work effectively. So that is why we need to consider this effective load, right? So this is 21 E CEB plus T upon this 21 V plus this CEB plus PT. So here you know V is pitch line velocity, this PT is tangential force, right? Then here B is phase width, right? So what is different or what is unknown or need to know is this C, right? So this C is nothing but deformation factor. Right, which is given by this K upon 1 upon P plus 1 upon G. Right, where K is constant depending on the form of teeth, right, whether it is involved cyclodel or 14.5 degree or 20 degree. So K is going to depend on the form of teeth. DP and EG are elasticity of pinion and gear, right, and E is nothing but sum of error between two meshing teeth. Right, so this is how we are having this particular dynamic load and the static load both, right? So this B is phase width, right, as we have already discussed. Now once you have idea about this, then based on this particular discussion you can have estimation of module, right? So now how this module can be calculated, because in
Sir,
the
what
yeah,
was C?
sorry,
What was that E?
E is error. Error is actually between this gears and what we can say this pinion. So whenever center distance is measured, this is not accurate. So there is some error, right? So that is EP plus EG, right? So there is some error in case of the location of center of both this pinion and gear, right? So this is that particular E, right? Some of
Sir, how to find the K?
sorry,
How to find the K, sir? Constant K.
K is actually documented based on experiment and all. They have decided the value of K for different types of form of teeth, right? Actually it depends on the form of teeth. Depends on the form, right, of teeth. So it is already having some tabulated value of this particular K. Okay.
Okay, sir.
So it is actually empirical design, right? So based on experimentation they are having this constant defined. Now the estimation of module. So actually module is important because based on that module only this all the other dimension of a gear are established. So that is why estimation of module based on beam strength, right? So now as we have discussed, this beam strength must be greater than the effective load which needs to be transmitted. Now if we consider any factor of safety, then we know that this SB is related with this effective load with this expression, right? Generally the factor of safety is in the range of 1.5 to 2, right? So this beam strength must be greater than the effective load, right? Then only failure is going to be avoided, right? So now
What is it?
sorry,
What is it notation?
notation, this is FS, factor of safety.
Okay.
Okay, so now as we already know this tangential load, is given by this 2mt upon this t dash, right? And this d is nothing but diameter, right, or pitch circle diameter. So pitch circle diameter can be given with module and number of teeth, right? So we can replace that diameter with this module into number of teeth. So if I further simplify, then it can be written as this 2 upon mz, this 60 into 10 raised to 6 kilowatt. As we know, right, how mt is described. We have also written this expression earlier, right? So with this, if you are aware already about this tangential load, right, and what we have seen in that first method, that how effective load is related to this tangential load is with this expression, right? P effective is nothing but Cs upon Cv into Pt. So if you put the values of this Pt into this equation, then you can have this Cs by Cv into this whatever this 2 will be cancelled, right? So this 60 into 10 raised to 6 kilowatt upon this pi mzn. So once you have this effective load, right, you can then go for SP, right, because SB we have already derived as MB sigma by, right, while discussing beam strength, right? So if we further simplify this, if we divide and multiply this equation with m, then m square b by m. This sigma b actually we can represent with that ultimate tensile strength divided by 3, right? As we have
Yes.
discussed, SUT by 3 we can write, right? Permissible bending stress we have seen, right? So SB can be represented with this particular expression, m square b by m as CT by 3 into y. So now once you have all this what you can say expression with you, then you can simply put the values of each expression, right? So if first we will put what is this SB, then it is nothing but this P effective into factor of safety, right? This we have seen. So this P effective into this factor of safety can be represented by this m square b by m SUT by 3 into y, right? Now this particular equation can then be actually further you need to write expression of this P effective, right, which we have derived here, right? What is this P effective? This you can put in this equation, right? So if you put this P effective in this, then it is Cs by Cv pi m, right? So let me write that is 60 into 10 raised to 6 is kilowatt, right, upon pi m zn, right, into Cs by Cv, right? So into this factor of safety. So that can be equated to this whatever this m square b by m Ct by 3 into this Lewis form factor. Right, so once you are done with this, then you can finally write for this module, right?
It's cube root of
Module will be then 60 into 10 raised to 6 kilowatt, right, divided by this pi zn, because this m will go this side, right, and it will become m cube, right? So this 60 into 10 raised to 6 kilowatt by pi Zn, right, into this Cs by Cv into Fs factor of safety, right? And this will undergo the denominator, this P by M is SUT by 3 and Lewis form factor. Okay, so this is how the module can be calculated, right? So this is how the estimation of module based on beam strength is given, right? So once you have idea about this, then we can also go for wear strength of gear, and then that estimation of module based on wear strength, right, that we can do. So
Sir, it is derived based on the velocity factor method only, sir.
sorry,
It is beam strength is derived based on the velocity factor method.
beam strength as such we have not derived with velocity factor, but in case of that effective load we are considering this service factor and velocity factor, right? Beam strength is this particular equation which we have derived with that Lewis form factor, right? This one, this is beam strength. Okay, hello.
Yes, sir. In this module is derived based on the velocity factor method, sir. Not using the Buckingham equation.
Which one?
But here we take in the effective load based on the velocity factor method, sir.
Yes, 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 yes. Here we have considered it based on velocity factor. Why? Because we have considered that particular effective load as that PT Cs by Cv, right? Here, this one, right? You are talking about this one, right? This is
Yes, sir.
velocity factor method. Yes, correct. Okay. So let us go further, right, to see this wear strength. So this wear strength of this gear tooth is based on that contact stress, right, or Hertz contact stress. So generally whenever these gears are in contact with each other, there are high stress, right, at the contact surface. So it will result in this stress area, right? This 2B, this is an electrical stress area at which this contact stress are acting, right, or compressive contact stress are acting. So basically this contact stress or this Hertz contact stress are given by this 2P upon pi BL, right? So this is how your this compressive stress which is acting at that particular area of 2B, right? Now this B can further be expressed with this relation of 2P 1 minus mu square 1 upon E1 plus 1 upon E2, right, divided by this pi L 1 upon D1 plus 1 upon D2, right, raised to 1 by 2. So this is how this B is represented. This mu is nothing but Poisson's ratio. Right, this P is the force pressing two cylinder as it is mentioned. This is the force, right, which is pressing the two cylinders. Right, and B is the half width of deformation, right, here as it is 2B, right, B is half width of deformation. right? And L is
Sir,
actual. Sorry,
what is the denominator term for B expression?
L is actual length. Sorry, one second. Yeah, what? Sorry, what were you telling?
What is that? What is that denominator term for B's expression?
It is pi L into 1 upon d1 plus 1 upon d2.
Okay, sir.
Okay. So this d1 and d2 are the diameter of this pinion and gear, right? E1 and e2 are modulus of elasticity for this pinion and gear, right? So now if you put the values in this equation of sigma c, right, and square that particular equation, then what we are going to get is something like this. Right, now if you put the value of Poisson's ratio as 0.3, it will reduced to this expression, right? Now here also some assumptions are there, right? Like this isotropic material and the stresses are not exceeded the elastic limit, right? And this particular radius of gear and pinion are much greater than that deformation zone 2b, right? So these are some of the assumptions. Now if you look at this figure, then here this gear and pinion are mentioned, right? So from this actually R1 and R2 can be mentioned as this dp dash by 2 into sine alpha, because this distance is dp dash by 2, right? As you can see, this distance is nothing but dp dash by 2 as mentioned here, and here we are having an angle of alpha, right? So this particular r1, as you can see here, it is mentioned like r1 distance from here to here, right? This distance is r1. So this distance is given by this dp dash by 2 sine alpha, right? This particular r1 is given by dp dash by 2 into sine alpha. Similarly for this r2, it is dg dash by 2 sine alpha, right? So we can write this actually here. This r1 is equal to dp dash by 2 sine alpha, and r2 is equal to dg dash by 2 sine alpha, right? So now once you have this relation, then you can find this 1 upon r1 plus 1 upon r2, right? Like 2 upon sine alpha in bracket this 1 upon dp dash plus 1 upon dg dash, right? So as we have defined that velocity factor, one more factor is defined, which is known as ratio factor. So that ratio factor is nothing but this q, which is expressed as this 2zg upon zg plus zp, right? So here, as we know, this diameter can be represented with module into this number of teeth, right? So this
Mm.
dp dash can be represented with this mzp and dg dash can be represented with mzg, right? So if you put this value into this ratio factor, then it is 2mzg, sorry, it will be uh, once in place of zg, dg dash by m will be there, right? In place of this zg, you can have this dg dash by m, and here this dg dash by m plus dp dash by m. So which will eventually results in this 2 dg dash plus dp dash, right? So if you are going to further simplify, then this 1 upon dp dash plus 1 upon dg dash is equal to this dp dash plus dg dash upon dp dash dg dash, right? So this is nothing but 2 upon q dp dash, because dg dash upon this dp dash plus dg dash is represented by that q by 2, right? Q by 2
Mm.
is
Yes.
dg dash upon dg dash plus dp dash. So here q by 2 is actually this dg dash by this dp dash plus dg dash, right? That is from the above equation only, q by 2. So simply this 1 upon dg dash plus 1 upon dp dash is 2 by q dp dash. Now if you put these values in that 1 upon r1 plus 1 upon r2, right, then you can come up with this relation that 4 by q dp dash sine alpha, right? Now if you consider that load, right, Pn, as we have seen, it is given by Pt by cos alpha, right? And if we consider that axial length almost equal to this face width, then your sigmas, if you put all this value into that sigma c square,
Sir, what is L?
m is module,
L, sir. L equal to
L,
B.
L equal to B, L is axial length of the cylinder which we are considering here. This is axial length of
Okay.
this cylinders, right? Axial length of this cylinders which we are considering equal to face width B. So if we put all these values into that equation, then what we will get is this 1.4 pt upon this b q dp dash sine alpha cos alpha 1 upon e1 plus 1 upon e2, right? Now this particular load stress factor we can consider factor load stress factor, or we can define that as again this k, which represent this sigma c square sine alpha cos alpha 1 upon e1 plus 1 upon e2, that divide by 1.4. So it is basically to simplify the above equation, right? So if you write this expression as load stress factor, then pt can be represented as this pq dp dash k. So here also, as we have defined that bending stress and then that beam strength, then here also if we want to consider that the failure should not occur, right? In short, whenever we are transmitting this particular tangential load, then that value of sigma c, which is here, right, in this K, this sigma c should not exceed, right, to a permissible value, right? So when that sigma c reaches that maximum, or sigma c reaches the permissible limit, then this value of PT is considered as wear strength, right? So as we have calculated that beam strength, right, based on that bending stress, here we have this wear strength based on this compressive stress, that is BQ TP dash K, right? So this maximum value of tangential force that can be transmitted without failure, right, as we have discussed. Now this ratio factor, actually what we have defined was for external gear, right? If internal gears are there, then this ratio factors can be represented as 2Zg upon Zg minus Zp. Previously it was plus, right, in the denominator, because we are considering internal gears. So for before we were considering external gears. So for internal gears, it is this Zg minus Zp in the denominator in place of that Zg plus Zp, as we have considered here, Zg plus Zp, right, here. This is for external gears, right? So this is how we are having this particular wear strength. So once you have this idea about wear strength, then you can have estimation of module based on wear strength, right? So based on this wear strength, as we have discussed that B should be greater than P effective, here this SW should be greater than P effective. Same way you can go for this estimation of module based on this wear strength, right? And you know how we have defined all this P effective and all. In the similar manner you can define here right. So once you have all these values with you, then you can put those values here. Also you can divide and multiply by this module. Here this MZP can be written in place of the TP dash, right? So it is m square V by m, then Q ZPQ, right? So if you put all these values of P effective and all, then here also you can come up with the relation, or you can define the module like this: 16 into 10 raised to 6 pi kW CS Fs divided by this Zp square MP V by m Q into K. So here also you can define this module based on this wear strength, right? Here actually they have also further simplified this K, right, which we have defined earlier, right, by putting the values of this E1, E2, and then alpha is the pressure angle, right, that is 20. Then this sigma C they have considered as 0.27 times this Fresnel hardness number, right, in terms of this kgf upon mm square. So they have simplified this as 0.16 bhn by 100 square by putting this values, right. So this is how we are having the estimation of module based on this different criterias. Now
For steel material, sir.
sorry,
K expression lastly given for the both pinion and gear made of the steel.
yeah, E1 and E2 both are considered as steel. I mean, they have considered that 200 what we can say 2 into 10 raised to 5 Newton per mm square, right?
Yes.
And pressure angle is 20 degree.
Profile, sir.
Sorry? Huh? Hello?
Okay, yes, sir.
Yeah. So now if we go to this numerical, then here they have asked that it is required to design a pair of spur gears with 20-degree full depth involute teeth based on the Lewis equation. The velocity vector is to be used to account for dynamic load. The pinion shaft is connected to a 10 kilowatt 1440 rpm motor. Now the starting torque of the motor is 150 percentage of the rated torque. The speed reduction is 4:1. Right, now the pinion as well as the gear is made of plain carbon steel 40C8 with this ultimate strength as 600 Newton per mm square. Now the factor of safety can be taken as 1.5. Design the gears, specify the dimensions and suggest suitable surface hardness for the gears. So can you try this particular what you can say example? Hello.
Sir.
So this 20 degrees alpha.
Yeah.
Sir,
Yes.
in designing of the gears, we mostly consider the beer strength or beam strength, sir.
Sorry.
Gears are probably failed in wear failing or strength failure, sir.
I
It may
couldn't
fail in wear or strength, sir.
couldn't hear you properly. What are you saying? Hello. Yes.
Gears most probably fail in wear conditions or strength conditions, sir.
Start condition. Yeah. That velocity factor, right? Yeah. So here, if you note down first given data, then power is given as 10 kilowatt, then RPM is given as 1440 RPM, then this gear ratio is given as 4, right? Gear ratio, let us say as 4, right? Now ultimate strength is given as 600 Newton per mm square and factor of safety as 1.5. Then starting torque is equal to 150% of rated torque. Right now, the number of teeth in this particular condition is generally considered as 18, right? So number of teeth on pinion is considered or assumed as 18. So based on that, number of teeth on this gear will be 18 into 4, right? This gear ratio, so it will be 72, right? And the torque, as you know, this equation or this expression will give you, right? So this kilowatt is with you, right? 10, and this RPM is also with you, 1440. So can anyone tell me this torque? MT? Anyone?
Sir, NP is speed.
Sorry?
NP.
MT?
No, sorry, NP, sir, denominator.
NP is this actually, this pinion rotation.
Okay, okay.
1440 RPM.
Is it 66,314 Newton mm?
It is around this 66,314 Newton mm, almost. Okay. All of you are getting this? Anyone else also has this answer?
Yes, sir. Yes.
Okay. Now Lewis form factor is this 0.308, right, for this given condition, right? For this 18 teeth, this Lewis factor is given as 0.308, and this service factor can be calculated with the starting torque upon rated torque.
So Lewis factor is mentioned.
Sorry?
Lewis factor, how did we find out?
It is actually from the design data book and all. It is not mentioned here, right? But from the
Okay.
design data book, it is 0.308. The service factor is 1.5 we can have, right? From this 150% of torque, right? Now, let us assume that pitch line velocity is 5 meters per second, right? So if you assume that velocity as 5 meter per second, then what will be your CV? Can anyone?
Sir, are we assuming
3 upon 3 plus V, right? Because as we are assuming that it is less than 10 meter per second, so it is 3 upon 3 plus V, means 3 upon 3 plus 5, that is 3 by 8, right?
So are we assuming this value 5 meter per second?
Sorry? No.
Are we assuming this value 5 meter per
Assuming
second?
this value, right? Assuming. So here actually we need to make some assumptions in this kind of problem, right? Again we need to assume that this B by M is 10, right? So now if we assume this and then we apply this equation that in order to estimate this module, then it is like this, right, as we have derived earlier. So I guess we are having all the values with us in order to calculate this module. So can anyone tell me what is the module? You have everything, right? This kilowatt power is 10 kilowatt. The CS is 1.5. Factor of safety is also 1.5. This number of teeth on pinion is 18. Speed RPM, speed in RPM is 1440. The CV is 3 by 8. P by M we have assumed 10. SUT also you have, right, 600. And this Lewis form factor is also we have from the data book like 0.308. So this will give you the module. So what are you getting as module? Anyone? Anyone has done the calculation? Four point 1.5. Yeah, it is around that only. Correct. So it is approximately at 4.15 mm. So we can consider it as 5 mm, right? So this m can be considered as 5 mm. So if we take that module as 5 mm, then diameter of pinion will be m into zp will be 90 mm, because 18 teeth are there, right? So dg dash will be m into zg will be equal to 360 mm, right? Because it is 5 into 72, and face width will be 10 times module, that will be 15. So once we have calculated this module from this particular what we can say relation, we need to go for actually check for design, because we have made certain assumptions, right? As you know, as we have made certain assumptions, we need to go for check for design. So let us see, this tangential load is 2 mt by dp dash. So it is this 2 into 66,314, almost around that, right? Divide by this 90. So it will give you, what is the tangential load almost? Anyone? Hello? Anyone with this tangential load?
1473.65 Newton.
It may be around 1473.65 Newton. Right, then this pitch line velocity is pi dp dash np upon 60 into 10 raised to 3. So that is pi into 90 into 1440 divided by the 60 into 10 raised to 3. So what is this pitch line velocity? Anyone? Hello. Anyone is there with answer?
So 6.785.
It is almost 6.785 meter per second. Right, so once you have this, you can calculate that CV, right? 3 upon 3 plus V, which is almost equal to 0.3066. Right, so once you have this, then you can calculate P effective, because you know that P effective is equal to CS upon CV into PT. So this CS is 1.5, CV you have calculated 0.3066, PT is almost 1473.65. So P effective is almost coming about 7209, right, Newton. Now you can also calculate the beam strength with this MB sigma B y. M we are considering 5, B is coming 50, sigma B is 200 and y is 0.308. So it is almost coming around 15,400 Newton. So as you know, this beam strength is more than the effective load, right? So you can also check the factor of safety. It should also be in the range of 1.5 to 2. So if you check the factor of safety with this beam strength upon effective load, then it is also coming around almost 2.14. So this is how this is satisfactory design, right? So once you are sure that whatever is designed that is correct, then you can go for calculating the Brinell hardness number, right, which is asked. So for that, if we consider that particular ratio factor 2Zg upon Zg plus Fp, because as you know, this Brinell hardness number is related to that wear strength, right? So this 2 into 72 is 72 plus 18, that is going to give you this 1.6. Now this wear strength is BQ dp dash K, right? So you know what is P, you know what is Q, right, 1.6, and we also have that P in diameter, and as we know, this K is given by this 0.16 PHN upon 100. We have written this expression, right, by some simplification. This K can be represented with 0.16 PHN by 100 square. If you give simplification, it will be almost this 1152 PHN by 100 square. Right, now as we know that this wear strength is having this relation with effective load, right? So we can write this P effective we have calculated as 7209, right, almost, into this factor of safety is 1.5. So now if you solve this, it will give you almost this VHN is equal to 306.39, right, or you can round it off 310. Okay, so is it clear? Hello? 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 Anyone?
Yes, sir.
Okay. So now let us quickly go through some of the questions from that gate. So here what they have asked is spur gear has a module of 3 mm, number of teeth is 16, phase width 36 mm and pressure angle of 20 degree. It is transmitting a power of 3 kilowatt at 20 revolution per second, taking a velocity factor of 1.5 and a form factor of 0.3, then the stress in the gear tooth. So how can you try this one? Hello? Hello? So first let us note down what is given, right? Like this power is given as 3 kilowatt, then RPM is given as 20 RPS, then form factor is given as 0.3, phase width is given as 36 mm, velocity factor is given as 1.5, and module is 3 mm, number of teeth is 16. So you need to calculate the stress, right? So how will you start? Hello? So
Sir, yes, sir. Trying.
so the very first thing you can do is you can calculate this PT, right? Because this is nothing but 2 into the torque divided by the diameter, right, of pinion. Here it is provided as what is the diameter is directly not provided, but you can calculate it from module and number of teeth. Okay, because module is provided, number of teeth is provided 16, so you can calculate diameter D is equal to M into T. Yes or no? This dP is equal to M into Z, right? 3 into 16, correct? Similarly MT you can calculate, right? How will you calculate MT? 16 to 10 raised to 6 kilowatt upon 2 pi n, huh? Yes, as it is in RPS, you can cancel this 16 because it is for RPM. When n is in RPM, the 16 is there. So MT can be calculated. Can anyone tell me what is this MT? Power is given in kilowatt, right? 23 kilovolt.
Is it 23,873?
Yes, it is this. One second, let me write. So it is basically this 23 point this 873, right, into 10 raised to 3 Newton Newton, right? I think all of you are getting this, yes or no? Everyone? Are you getting this? Hello?
Yes.
Okay, so once you have this
Yes, sir.
yeah, once you have this torque and diameter, then you can calculate this PT. So what is PT then?
Sir, form factor will be included in?
This form factor will be there in the beam strength, right? Hello? Can you hear me? Hello, can you hear me? Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. So sorry for the interruption. Yes, that particular form factor and all we will consider while considering this beam strength, right? SB is equal to this MB sigma By. Okay.
Yes.
Yeah. So yes, for now this PT you can calculate. So can anyone
The
tell me?
screen is not. Sir.
Okay. One second. Now is it visible?
Yes, sir.
Okay. Yeah. So yes. So now can anyone tell me what is this PT?
994.71 Newton.
994.71 Newton almost, right? Now, so as we know that
71 Newton.
71 Newton, so that is what I have written, right? So in order to be that safe design, that whatever this effective load we are having, right, it must be less than, as we know, this effective load must be less than the beam strength, that we know, right? Yes or no? Hello.
Yes.
So what is this effective load that is given by this?
Yes, sir.
Yeah, so it is given by this TCV by CS, right? So for that, if you now put this SB as this MB sigma by, then you will be able to calculate this sigma b, because you are having all other values with you. As service factor is not given, you can consider equal to 1. CV is given as 1.5. CV is given as 1.5. So, are you getting what we are doing?
Yes, sir.
Yeah, so now you have all the things with you. Module is given as 3, right? Module is given as 3. Face width is given as 36 mm. Y is given as 0.3. PT you have already calculated, right?
Sir,
Yeah.
sir, if we had the service factor, then we will include it in the denominator.
Yes, sure. So from this sigma b can be calculated. So what is this?
46.05 Newton per mm square.
Yeah, it is almost around this 46 megapascal. Right, so let us see. Yeah, in option we are having this 46 megapascal. Okay, correct. So let us go to the next. Here a 20-degree full depth involutes per pinion of 4 mm module and 21 teeth is to transmit 15 kilowatt at 960 rpm. Its face width is 25 mm. The tangential force transmitted is, and then the given that the tooth geometry factor is 0.32 and combined effect of dynamic load and the light factors intensifying the stress is 1.5, then the minimum allowable stress for the gear material. So let us see this one by one. So can you try this?
Sir, here this 1.5 is included in numerator, no, sir.
Sorry, 1.5?
Is included in the numerator while calculating this as a factor.
Yes.
Sir, actually, there are a lot of factors, no, sir. Like for example, CVCS. Like, how can we remember like which will be included? How?
That you have to actually remember, right, here in this case.
Sir, because like certain times it is not directly given, no, sir. Like which is what is the name of the factor instead?
I mean, they are providing the name, right? They have clearly mentioned that velocity factor is 1.5, right? And whichever factor is not provided, you can assume it as 1.
Yes.
Okay. So here, how will you start? If you note down first the given data, then module is 4 mm. Then this number of teeth is 21. Then speed is 960 rpm. Then this pressure angle, or we have considered alpha, right? So that pressure angle is given as 20 degree. Then face width is 25 mm, right? So your transmission power is also given as 15 kilowatt. Now as we know, power is nothing but T omega, right? So this torque can also be given as this tangential force into radius into omega, right? Now radius can be calculated from this data, right? mt by 2. R can be calculated with this mt by 2. So m is 4 into 21 by 2, that will give 42 mm. Radius will be 42 mm, right? So if you now put all the given data, then you will be able to calculate the tangential force, I guess. Right, because R is 42 mm, omega you can calculate from 2 pi n by 60, and power is given as 15 kilowatt. Yes or no? This 15 kilowatt is given, right? Need to calculate this tangential force. So can you tell me what is this PT? Anyone?
3005
52, right?
355.
Yeah, it is almost about this 3552. So this option will be the correct answer. Now what they are asking in this next one is minimum allowable stress, right? So for that they have provided some more data, like they have provided that factor as 0.32, then this combined effect of this dynamic load and allied force, right, are intensifying the stress by this 1.5. So it means the factor of safety is 1.5, right? So once you have all this data, then here I guess one more important thing is when you are defining this sigma b, because now you can apply that as P, or we can say that Ft. It is not for that strength, right? It is just for this particular case where this applied tangential load is this 3552, right? So for this, how we can write that mb sigma b y.
excuse me, sir.
Sorry.
Sir, they have given intensifying the
Yeah.
stress means allied factors intensifying the stress is 1.5.
Yes.
So is it analogous to service factor?
No, 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 no. It is related to the factor of safety you need to consider, right? Because as you know, factor of safety is equal to this maximum allowable stress, that is mb sigma by upon this particular tangential force applied at a particular time, right? So when this intensifying factors and all are applied, it means you need to consider this factor of safety, right? So for that,
Okay, sir.
yeah, for that particular case you need to consider this, right? This is the beam strength upon this tangential stress at a particular point. So if you use this particular relation, then you have this PT calculated as 3552, M is with you, right, 4, then B is there 25, face width is given, then sigma B you need to calculate, Y is given as 0.32, and this factor of safety is given as 1.5. So from this you can calculate sigma B. So can anyone tell what is sigma B?
166.53.
Yeah, so it is almost around this 166.5 megapascal, right? So let us see, it is there, see this 166.5. So let us go to the next one. Here a spur pinion of pitch diameter 50 mm rotates at 200 radian per second and transmits 3 kilowatt power. The pressure angle of the tooth of the pinion is 20 degree. assuming that only one pair of teeth is in contact, the total force exerted by a tooth of the pinion on the tooth on a matting gear is. So here it is very simple, right? So what they are telling is they are having this one tooth, right, in which force is applied along that pressure line as we have seen, right, and along the pressure line when you are applying, then you will have this as your tangential force, and this angle is given as 20 degree. So once you have this particular data with you, diameter is given as 50 mm, then omega is 200 rps, then this power is 3 kilowatt, and phi is 20 as already we have mentioned. Now from this you can calculate the torque directly, right, because a torque is equal to power upon omega. So power is given as 3 kilowatt, omega is 200, so this gives torque as 15 Newton meter. Yes, is it correct?
Yes, sir.
So once you have this torque, then this particular Ft or Pt, right, tangential force into radius, is equal to this torque 15 Newton meter. So radius will be 25 mm, right? So this Ft into 25 is equal to this 15 Newton into 10 raised to 3 mm, right? So once you convert this to mm, you need to multiply it with 10 raised to 3. So it will give you Ft as
600.
600 Newton. So this Ft is 600 Newton. So what you are asked is the total force, right? Total force exerted, right? So in case of finding this total force, you have a relation, right? This total force is equal to this Ft upon cos phi. Yes or no?
Yes.
So it is 600 by cos 20. So what is this?
638.5.
638.5 Newton. So here you will have 638.5 Newton. Right, let us go to the last one. So a steel spur pinion has a module of 1.25 mm, 20 teeth and 20 degree pressure angle. The pinion rotates at 1200 rpm and transmits power to a 60 teeth gear. Now the face width is 50 mm, Lewis factor is 0.322, dynamic factor is 1.26. Now the bending stress induced in a tooth can be calculated by using the Lewis formula given below, right? Lewis formula is mentioned as sigma is equal to kV Wt upon Fmy, right? It is mentioned where Wt is tangential load acting on the pinion. If the maximum bending stress experienced by the pinion is 400 megapascal, the power transmitted is in kilowatt we have to calculate. So now how can we approach this? So first, if we note down the given data, the module is 1.25 mm. The number of teeth on pinion is 20. Then module is 1.25 mm. Then this angle is 20 degree. This NP is given as 1200 rpm. Then this ZG is 60, right? So once you have all this, then what you need to do is you can then equate that effective load to the beam strength in order to calculate the this particular tangential load, right? as we have done earlier, this PT into CV by CS will be equal to this beam strength, right? What is that beam strength? MB sigma B Y. So you are provided here with that particular, what you can say, data, right? Again, that PT into this 1.26 is this particular kV, right? That is CV. So this PT into 1.26, again CS is 1 as not mentioned. Then module is given as 1.25, right? Then this face width is provided as 50 mm. This face width, let me check. Yeah, face width is 50 mm, right? Then this sigma B is provided as 400, and then that Y is provided as 0.322, right? If you see this, yeah, Y is 0.322, sigma B is 400. So from this you will be able to calculate PT. So can you tell me what is this PT? Hello.
6388.89.
Yeah, it is almost around 6388.89. Now once you have this force, then power transmitted can be calculated, right? Equal to this tangential force into velocity. That is this PT. You can mute yourself.
Yes.
That by dP and by this 60. dP can be calculated from M into Z, right? M is module 1.25 and Z number of teeth 20. So dP can be calculated, and NP is anyway provided as 1200. So if you use all this, then you will be able to calculate the power transmitted. Can anyone tell me the power transmitted? Anyone?
Ten point zero 10.036 kilowatt.
It is almost around 10 kilowatt, right? So you can write right up to this 1 decimal place as 10 kilowatt. Okay, so we are keeping it up to here.